Loops and 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 loops. B fields, B fields, B fields, B fields. Okay, what we're going to look at here is the derivation of a toroid. Now, what is a toroid? Imagine you have a solenoid where you have these wire loops like this, but you take your wire loops and you wrap them in a loop. So it's loops of loops going around, okay? That's a toroid. And we see one in the picture right here. This is loops of loops, and they've put a piece of metal inside of this to amplify the magnetic field. So how could we actually figure out what the B field is inside of this toroid, this turned over solenoid here, this kind of donut shape? Well, here's another picture of a toroid. What we have here are X's and dots. This means that the X's, the B field is going, or the wire is going into the page on the top, and then the wire is coming out of the page down below. So we actually know that this is the direction of the current. This is a current going in, and then this is a current coming out. Well, what we're going to do to find the B field on the inside of this toroid, we're going to use Ampere's law. And Ampere's law is actually pretty straightforward for a toroid here. First, what we need to do is we need to create an Amperian loop. So looking at these shapes here, if you were to guess an Amperian loop, it might be a good idea to guess a circle as your Amperian loop. The sound effects are sweet. The circle looks like garbage. Activate better circle. Boing. Boing, boing. Okay, that's a better circle. Not much better, but better. So if that's my circle, and it's centered on the center of the toroid here, on the inside, so it's centered right here, then if I give this a direction, we can just use Ampere's law to figure this out. We know for Ampere's law that the closed loop integral of the B field dotted with some path vector of the Amperian loop is going to equal mu naught times the current enclosed. And in this case, we've seen this in our examples, the B field is a value, so we pull it out, and we integrate over ds, and we're going to see here that we're going to have B times 2 pi r equals mu naught times the current enclosed. Well, the real question is, what is the current enclosed here? Because I have the current I existing not once, not twice, not thrice, but 4, 5, 6, 7. I have some number of turns here that exist. So I don't just have one current I have that current I over and over and over again, and actually have it for as many loops as I have. And if you recall in the solenoid derivation, we count the number of loops as big N. So our total enclosed current here is actually going to be I multiplied by some number of loops N, which means that our B field inside of the toroid is going to equal mu naught I n over 2 pi r. And this actually means that when we are close to the center of the toroid right here, we have a very small value of r. We actually have a very large B field, and as we move outward, that B field decreases as a 1 over r value there. So it's kind of neat. The B field isn't constant as we move out the toroid. It's actually changing as a 1 over r value. Okay. Ampere's law here also shows us something interesting. If we created our Amperian loop in the middle, anywhere in the middle, we wouldn't have a current here, and that means the B field equals 0. Furthermore, if we created an Amperian loop on the outside, our B field would also be 0. The reason why it would be 0 is we'd still have B times 2 pi r equals mu naught, but our current enclosed would be N times I going out of the page minus N times I going into the page, because I have currents going in and out here from the two different directions of the current. And since they're the same amount of current in the same number of loops, these subtract and equal 0. So we'd once again see on the outside our B field equals 0. So inside of the center of the toroid, in this region, we have a B field of 0. Outside, we have a B field of 0. It's only in this kind of the actual donut part itself of the toroid that we get a B field as given by this equation. So a kind of straightforward example, if we think about it, we just need to be careful about toroids in similar ways, and that also makes sense that the inside and outsides have to be 0, because imagine you took a solenoid and you just kind of wrapped it on itself. The outside of a solenoid is a 0, and as you wrap it around, well, you've created a 0 on the inside and a 0 to the out. So that's what's going on here. But that's our toroid equation for the B field, and with that, we are finished. Adios. Take it easy.